sorry. Apologies there. I forgot to resume recording. So A is 32768 AAA, B is 32768 BBB, and C is 32768 .CCC. So how the switches A, B, and C elect the root bridge is it looks at the priority number first, which is a default number of 32768. When there's a tie, and there will be a tie if it's a default, then the kicker is going to be the MAC address. MAC address is run from 0 to F. And you're going, how can it go from 0 to F? Well, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay. So lower is better. So any numbers are going to be lower than the sort of alphanumeric A, B, C, D, E, F. So F is sort of the equivalent of 15. Text. Okay. So the rule with spanning tree, when it comes to election, how spanning tree decides every election is lower wins. Lower is better. Okay, so all of a sudden, switch A is the root bridge. Why? Because AAA is lower than BBB, is lower than CCC. Okay, so switch A is the root bridge. And the other switches accept that. I am the root. Okay, then B says I must find the best path back to switch A. Now remember the costing system. If it's Ethernet, which is 10 meg, Ethernet will have a cost of 100. If it's fast Ethernet, which is 100 meg, fast Ethernet has a cost of 19. If it is gigabit connection, it has a cost of 4, and 10 gig has a cost of 2. Okay. Again, lower wins. So you can see here, the faster the link, the lower the cost. Okay, so the speed of the link is inversely proportionate to the cost. Faster the link, the lower the cost, because lower wins. Lower is better when it comes to networking. In some aspects, not all. Okay, so let's say these are gig links. Okay, even though they're Ethernet here. Let's say they're gigabit. You're not going to have Ethernet connections in this day and age. Not trunk links, Jesus, no. So let's say these are gig links. So B says the cost for me to get to A is 4. Where it'll cost 4 here and 4 here, well, that'll be 8. So B's best path back to A is across. And it will give this name, this ETH 0/0 a name. It will say you're my root port, because that's this port switch B uses to reach the root bridge.
If two routes are the same cost, which is used?
If two routes have the same cost, well, you're not going to have it here because
I know they won't here because there's only 3 switches, but if there was 4, say, and both passes.
Yeah, it's a great question. Great question. Let me come to that. What we'll have a look here. Hold that thought. I'll come back to that in a minute. Yes, John.
Yeah, it's just curiosity. It doesn't really.
Yeah, no,
it doesn't matter.
No, I'll have a look at it because there is an important point I want to discuss on it. And so that's the root port there. If this is then this is going to be the root port here. So this is the port here. So this will be root port. This is C's root port, yeah. Because that's a port C uses to reach the root bridge. The root port itself here, the root switches, which is switch A's, root ports are going to be designated ports. Remember, you must have a designated port per link. And when there's a tie then between switch B and switch C, because this is your redundant connection. This is your redundant connection. So one of these ports is going to be blocking mode. Which one will it be? Will it be E00 on switch C, or will it be E01 on switch B? Well, it's going to be switch C will be blocking because switch C has a higher bridge ID. 32768 CCC is higher than BBB. So this port here is going to be blocking. And if that port's blocking, then this one here is going to become designated. Any questions on that? So what'll happen is traffic now, let's say we just give you the name, between Tom and Bob will go via switch A and down this way because this link is blocked. Can't use it. Let me just close that off, open up Paint again. Ah, that didn't do it. It must have saved it for some reason. So very quickly, we switch A. There's a route. This port is designated. This port is designated. This port is route port. This port is route port. This port here is blocking. And this one here is designated. So traffic between PC here, PC2, and PC3 is going to be going out this way and down here. Okay, something happens, one of these links, this port that wasn't blocking will go blocking, listening, learning, and forwarding. All right. And we'll discuss that later on when we actually see it face to face. So what I'm going to do here is, before I do this lab, I'm just going to show you another lab. Packet tracer. So now I get two switches. Switch A, and switch B. Right, so that's just SWA and SWB. Okay, and we're going to get two links here. Okay. Right, let me just draw it out. Because if I do it on this, yeah, okay, just draw it out. Let's say we have two switches here. So we have switch A here, and we have switch B. Okay. SWA and SWB. Okay, and we've got a connection going from A to B, trunk link here, and we've got a trunk link here. And let's say this is ETH1 to ETH1 and ETH2 2 to ETH2. Okay, let's say switch A's MAC address is AAA and B's MAC address is BBB. Okay, so which switch is going to become the root bridge?
A.
A, yeah. So then B says, well, okay, we've got redundant connections between B and here. So B says, I need to find the best path back to A. So it looks at this costless system. So this Ethernet, let's say this is Ethernet and has a cost of
4.
Well, let's say this is gigabit connection, right? So this is gig link, gig 1 and gig 2. And this is gig 1 and gig 2. So gigabit links have a cost of 4. So it costs B 4 to get to A at gig 1, and it costs B 4 to get to A out gig 2. Well, how do we, which port gets shut down then? Which port gets blocked? It costs the same amount for B to reach A.
Well, would the MAC address not be the kicker, as you always say?
Then the MAC address, no, because the switch is B, like switch A's MAC address is AAA, so it becomes the root. Then the process is the other switch. Well, we've only got one switch here with switch B, says I must find the best path back to switch A. And how switch B determines the best path back is the speed of the link. So it says, okay, well, it cost me 4 to get to A out this interface, but it also cost me 4 to get to A out this interface. One of these ports is active and one of the other ports will be blocking. Which is it?
G1 active and G2 blocking.
Why?
Lowest is best.
Lowest is best. Very good. G1 is a lower interface number than G2, so therefore G2 will be blocking. That's it. That's again, that's it, like a kicker. So it looks at the interface G1, G2. Okay, well that's blocking. Well then this is going to become active. What port will this be called?
Root.
Root port, because the support B uses to reach the root bridge. This one here is going to be
Designated.
designated. This one here is going to be
Designated.
designated, because there's root bridges are always designated ports, and then this one here is going to be blocking.
Very good.
Cool, good stuff. Gets a little bit clearer the more we do it, the more we do it, the more we do it. Yeah. So let me just start connecting on here, and documenting our switches. So I have no idea which switch is root bridge here. So let's console into each one. Switch A, switch B, switch C. Okay, so first of all, we need to see if they're trunks. Show interface trunk. Ah, we don't have trunk links set up. So we need to set up trunk links. So what we can do is we'll just do show IP and brief. Okay, well, they're all up, but show VLAN. So E0/0 and E0/1 needs to be trunk links. So if I do show interface ETH 0/0 space switch port, then you can see here it's in access operation mode. So it says I'm in access port because it's dynamic, is auto, it's auto negotiation. We talked about this. So if all the switches are auto negotiation, then they're not going to become trunk links. Oh, so we go in. Config space T. These multi-layer switches are a little bit different to set up. So I have to go into the interfaces, ETH 0/0. If I do switch port mode trunk, it's not going to work. It says because your encapsulation is set to auto. So I need to change the encapsulation. Switch port trunk encapsulation .1Q. And now I can do switch port mode trunk. I don't know why to do that. It should be able to, that command switch port mode trunk should be enough to force that trunk link, the ETH 0/0 into trunk link. I'm going to do the same with ETH 0/1. There's it. Interface ETH 0/1, switch port trunk encapsulation .1Q, switch port mode trunk. Now what will happen is, because the other end is auto, can I just clear all that? Okay, so because the other end is auto, what will happen? So I've set this link here. We've hard coded this link as a trunk port. There it is. That's trunk. This is auto. What's going to happen now? The link here. One end is trunk and the other is auto. It will trunk. But the problem was both ends were auto. So when both connections, ends of the connections are auto, it won't trunk, it'll say as an access port. But if you set up one link on one switch as being trunk, then everything else will follow. Now, I don't like doing it. I don't like using auto at all. I like to go in and hard code each connection as a trunk link, because it means that you have less of an issue. You don't have that risk. So I'm going to go into ETH 0/0 and ETH 0/1. Now remember, you can use the range command. Interface range ETH 0/0 space hyphen 0/1. Oh. Space hyphen slash, it could be one actually. Yeah. Interface range ETH 0/0 space hyphen space 1. And now switch port. Oh, encapsulation. Encapsulation .1Q space switch port trunk encapsulation. Yeah, that should be. Why is that not working? Switch port encapsulation trunk encapsulation .1Q. Okay, it's done on B, and then I'm going to do in C. I'll just copy this in here. Cross enable for big space T. Switch port trunk encap .1Q. Switch port mode trunk. Switch port trunk encapsulation .1Q. Switch port mode trunk. Now we have 3 trunks. Just to verify it again, go into A, show interface trunk, and you can see the 2 ports in there. This one here, show int trunk, 2 ports in there, show int trunk. Okay. Let's map out our VLANs. Okay, let's map out. So we'll say, let's check in here, do show span. I don't know which is which. Okay, which port, which switch is root bridge? Let me just see if I can. Can we tell which switch is root bridge? Anyone?
I'll look at all three switches to see which one is best. All we see is switch B.
You don't have to even look at the three switches. You just look at
Oh,
switch B
right.
here. Sorry, based on this information here.
Switch B. Is it?
So I'm currently connected to switch B. Oh, that's probably even better.
well, the cost there is 100.
So that means it's just an Ethernet port. So it means it's
Yeah.
10
Yeah.
meg connections.
Priority 232.769. One up in the VLAN.
Look at the port types.
Okay. Low, yeah.
Oh, A is the root.
Lower,
Why did you say A is the root?
because lower is best.
Because it has
the root
root in under the role.
The role, yeah. So ETH0, so I'm on switch B. So ETH0/0 is a root port. So that says that this is the port switch B uses to reach the root bridge. So if this is a root port, then that means that switch A is a root bridge. Because you know, if 0/1 was a root port, now don't look at don't concentrate on the other ones. Like you know, just you really only should be looking at the trunk links here. So you should only be looking at each 0/0 and 0/1. If 0/1 was a root port, that would mean switch C was a root bridge. Does that make sense? So this is on switch A or switch B here. So it's saying that this is the port used to reach the root bridge. Okay. Guys, let me know if you have any questions on that.
That's good.
Okay. So if we go into B then, are we going to A? Or we do show span? Oh. Trying to extend this out here. Well, there we get this okay, perfect. Did I get this one perfect? So for some reason, so the show span here. Okay, so again, ETH. This is how do we know this is where the root bridge here? This bridge is the root. Switch A.
Yeah, 0/0, 0/1 are both designated.
Yeah, exactly. Yeah. So this is switch A. Okay. And 0/0 and 0/1 are both designated ports. Exactly. We're going to switch C. Show span. You can see here straight away it says, well, one of the ports is alternate, is blocking, which is going to be 0/0 on C is blocking, because switch C has the highest MAC address. Okay, and the way but this kind of makes sense because when I set up this GNS, I had switch A, I added this first. The first switch I took out, this was it. So this had a lower MAC address. Then I added switch B, which had a little bit of a higher MAC address, because each MAC address increments on the program of GNS. And then I added switch C last. So the first switch I used is the oldest one. So therefore it has the lowest MAC address. So therefore it's the root bridge. So let's just run, let's connect in. I'm going to run this here again. Oh, let me just console into this. PC2, and I'm going to console into PC3. Give them IP addresses. Excuse me. Sorry about that. So IP 192.168.1.2 and PC3 IP 192.168.1.3. Okay. So I'm going to go back here and ping space 192.168.1.3 space question mark. What do I want to do? I want to give it a count. Ping space 192.168.1.3 space C space, let's say 1000. So I'm 10,000 pings across. So we'll go back in. So again, the one that's blocking is E0/0. I'm going to put in here blocking on it. Let me put a little note here. Just put it blocking. So traffic between PC2 is going to switch A and is down here. So let's just run Wireshark. Skip version. And you can see it. Let's see if I can filter as protocol. And you can see here Spanish tree, SCP. So this is my BPDU. 802, this is going across your VLAN. And has your information. Your bridge ID 32768. And then that's the MAC address. See, this is how the switches elect the root bridge. The max age is basically the 20 seconds that a switch port will stay in blocking. Very little information on it. These come every 2 seconds. You got a BPDU to which is used to identify the root bridge. So it says the root bridge's MAC address is here. So it's just pieces of information. Okay. So what I'm going to go do is we know switch C is blocking E0/0. We know our pings are running across. Let's go into E0/1 on switch A and shut down that port. So config space C int E0/1 shut down. Now let me just get a timer up here. Stopwatch. Last time it was 40 seconds. And just enter. Oh, where's the timer? Start. Okay, so leave the timer running there in the background. Let's go back to here. We're getting our timeout. So what's happening now with the switch port, switch C, if I do show span here, it's listening. You can see it here, it's listening. It's listening still. Listening. Learning. It's learning. It's still down. It's learning. Still down. Still down. There we go. Stopped it. 55 seconds. So that's how long it took for it to go from listening to learning to from blocking first to listening to learning to forwarding. And I talked how to prevent that from happening is what? Is you need to update your spanning tree to rapid spanning tree. Spanning tree mode rapid. B, fixed T, interface, or spanning tree mode rapid. And C, fixed T, spanning tree mode rapid. One more thing you should always do as well is have the connections port fast. So 1/1, 1/1, and 1/1 should also be port fast. So go big T, interface ETH 1/1, spanning tree port fast. What does that mean? It means the port comes up fast. Why? Because it's not checking for your blocking listening. It's not checking for BPDUs. It's not. It doesn't go when you connect a laptop into your port. It comes up straight away. And ETH 1/1 on PC3 will do the same. Big T, ETH, interface ETH 1/1, spanning tree port fast. Okay, we'll do the same thing now. Leave those pings. Let me go back into switch C or back. Where did we do it? Where did we shut this off? We shut it off on A0. Is it E? Sorry, we shut it off on E0/1 on switch A. So we need to go back in there. Exit, interface, ETH 0/1. No shutdown. Okay. So now we're running rapid spanning tree. How do you know you're running rapid spanning tree? Well, if I go into switch A here and do show span or STP, yeah, rapid spanning tree. Whereas before, IEEE. Okay. Now I have to say, I don't know how like, because it's a GNS, it's not using, you know, this isn't like the difference between I don't know how accurate this is going to be in terms of its spanning tree or rapid spanning tree. So we'll just have to find out. Okay, well, we'll check it out anyway. So let's do the same thing. We went into ETH 0/1 on switch A. Do the same thing. Interface ETH 0/1, and I said put down. Okay. Didn't look like anything happened.
I think you were on switch B. You were when you did that shutdown.
Oh crap! Yeah, switch B. So 0/1. Actually, nothing would have happened there. Yeah, good call. Let me go back in there again. Int ETH. Oh, just do no shutdown. I can switch A again. Sorry. So base T int ETH 0/1. Let's just make sure the pings are running. Yeah. Shut down. Oh, we're getting a timeout. Let's go to switch C here. So span. She's blocking. Yeah. So if this was a real switch, this would have come up straight away. Yeah, even though it's running rapid span tree. Yeah. Not too bad still. But you really, if it was a real switch, you'd only have, you know, Well, about 15 seconds, not even. If it was a real switch, it would be just instant. Okay. All right. I want to talk about another thing here. Actually, might as well you use these switches here. Let me just. Actually, I'll open up Packet Tracer. It's easier to do this on Packet Tracer. Actually, no. Let me just no. I'll use GNet. Let me just clear some of this stuff off here. So I'm going to delete some things here. If it works for me. Oh, okay. Delete. Delete this one here. Actually, don't need these PCs here either. Okay. So we got switch A, we got switch B, and I might add in a router here as well. Okay. So let me just put in a router here. Between two of them. Or one, right? Okay. So let me just connect in here. ETH 0/0 to gig 0/0, 1/0 to ETH 0/1. So you have switch A over here, you got switch, and you got switch B. Okay. Let me just start up these first. And I'm going to console in here, switch B. I'm going to console into the router. And I'm going to console into switch A. Okay, cool. Good stuff. Follow. Great. So if I go into switch R1, right? So if we, I'm going to keep this down here. Let's say, for example, I have I have to map out this diagram, and I'm in a different city or I'm in a different building, and then the comms room, and I don't know what's connected into what, and I can't walk down and check because the comms room is far away from me. But what I can do, there's a process called CDP, and CDP stands for Cisco Discovery Protocol. Okay, it's a layer 2 messaging protocol. Layer 2 messaging protocol that allows you to discover directly connected Cisco devices. Very, very useful. This is a tool that you will be using if you're in a data center or if you're a network engineer, because it's very, very useful for connecting, for finding out where devices are in your network, what devices is connected into what, and mapping it out. So for example, you got switch B here. Okay, so what happens is CDP, Cisco Discovery Protocol. Basically, they send messages to each other every 60 seconds. They're called CDP hello messages. Hello, hello, hello. So when R1, and what the CDP message will contain? The CDP message will contain things like the host name, switch B. It's what it can do, what it can process. For example, it's the switch here. So I'm a switch. And its local interface, E0/0. It will have a hold down time. It sends all of this information to R1, and then R1 puts that information in a little table. called CDP table. So if you log on to R1 and you type in show CDP neighbors, you will directly see switch B and switch A. Now, CDP shows you directly connected Cisco devices. They have to be directly connected and they have to be Cisco. So let me show you that. If I log on to R1, I'm going to do show CDP neighbors. Okay, this, right, this mightn't work because this operating system isn't exactly a Cisco operating system. It's a Linux-based OS. Like if I can click on it here, maybe you can see it here. You can see hardware Cisco IO, but it's a Linux. See IOU image. It's a Linux-based layer 2. Now let me, or maybe that's. Let me just check. It could be turned off. Config space T CDP space run. Maybe listening into it on Wireshark. You can see our Spanish stuff being sent over. I'll log into switch A here. Exit. So CDP neighbors, big space C, CDP space run. No, I'll try another one. So LLDP neighbors. Oh, I have to enable LLDP. I don't think LLDP will work on R1. Let me directly connect switch B to this guy here. So basically, I think what's happening is because these are Linux-based operating systems that I don't think they're participating in it. No, nothing on it. So LLDP neighbors. No. Let me do this. I'm going to do this on packet tracer. Okay, switch A, switch B, and I have. Let's just give these names the different names. So let's get this say apples, and this switch here is called oranges. Okay, and I'm going to get a router in the middle. $141. Connect in. Let's say gig 0/1 to gig 0/1, gig 0/0 to gig 0/1. Okay. Let's go into the routers here first, just to enable it. Enable config space T interface gig 0/0, no shutdown. Exit interface gig 0/1, no shutdown. Okay, now I need to give these switches host names. So I'd say enable config space T host namespace apples, and this guy here. Enable config space T host namespace oranges. Okay, let me just fast forward time here in this. Okay, so let me log on to this router here and say enable show CDP neighbors. Now, here we go. Look, so we can see this information. So basically, what we're seeing, the router says there is a device connected to me on my local interface of gig 0/0 with a hold down time of 140. I'll talk about that. I'll talk about the hold down time in a minute. Its capability is a switch, which Apple's is a switch. And sorry, Apple's is over here, yeah. And the type of switch is 2960, and the remote port is gig 0/1. So using that information, you can map out what devices are connected into. Does that make sense, guys?
Yep.
So the hold down time is basically when these switches are sending hello messages every 60 seconds, the hold down time is basically how long the router will keep that information in its table for. So by default, the hold down time, it's a countdown timer, and it's 180 seconds. So this so R1's CDP table is held in its database for 180 seconds, and it counts down 179, 178, 177, and it keeps counting down. And let's say something happens to this link. If it doesn't hear anything back from switch B, we're calling it switch B in this case, in 177 seconds, well then switch B is removed from its table. So the hold down time is 180 seconds. So how many CDPs will switch B send in that time?
90.
So if it's 180 seconds and it's sending a hello message every 60 seconds.
Obviously,
So basically the R1 says, if you don't respond to me, if I don't hear anything from you back in 3 CDP hello messages, 3 by 60 is 180, then I'm going to remove you from my table. So the table gets reset. So if what happened is, let's say this went offline for 40 seconds, the link. How far will this CDP table go before it gets reset? Well, typically it will go as far as 40 seconds. So, and then what will happen is it goes to this 140. Switch B sends another hello message, and then it gets reactivated. Let me show you. So, oh, this is good. There we go. Watch now. So you can see here. Look at oranges here. Orange, the hold down time went 120, 1, and then 179. What happened? Because the hold down time in normal operations is going to go as far as from 120 before it gets another CDP hello message. That was a bit confusing. I'm going to just remove that statement there, but I said with the 40 seconds, that's going to be a bit confusing. So basically, it sends hello messages. Switch B is sending hello messages to R1 every 60 seconds. The hold down time starts as soon as it gets a message. The clock starts at 180 and counts down. In normal operations, if everything is okay, it will go as far as 120, because 180 minus 60 is 120, and then switch 2 will send another CDP, and then it goes back 180, 179, 178, and so forth.
why is there different hold down times for different ports?
It doesn't have different hold down times. The hold down time is the same. Well, what happened was, yeah, I see what you mean. So basically, when I activated Apple's first, I connected Apple's in, then I connected Orange's in. So basically,
Let's get right.
it was just up quicker.
Yeah. Okay.
So there's always going to be whatever here, 5 seconds in the difference. See, it's consistently been 5 seconds in the difference. What happens if I send, well, I'm going to go into this switch here, okay? And I'm going to change the host name of apples to bananas. Apples is now called bananas. It identifies itself as bananas. Okay. So what's going to happen? Look. Apples came online because CDP said, because the switch that was apples was sending CDP hello messages and then stopped sending hello messages from apples because apples is no longer around. Apples is now called bananas. So bananas started sending these CDP hello messages and apples was going to time out. This is going to go to 0. Now it's basically apples is but the same switch as bananas. So the router identifies the switch by the host name. When we changed the switch's host name from apples to bananas, the router put in bananas in the CDP table, but didn't remove apples straight away until the hold down time expires. So when this hold down time goes to 0, well, then apples will be removed. Let's check this out now. Now apples is gone. Is that okay, guys? Let me log on to my GNS3, see if anything happened here. CDP, let's log on here. No, I'll have a look into that, see why it's not. I might have to get an operating system. I'll see if I get an operating system with a switch, a real switch, and connect in. All right, that's it. That's it for the